think we can start. Hello. I'm Michael. I work for Software Mill. And for start, Software Mill basically is a very unique company because, first of all, we don't have any bosses. There's a fully flat organization structure. And second thing is we don't have any offices because everybody works remotely. But today I would like to guide you into the big data world. And biggest hype around the big data took place already a few years ago. Then this hype moved more to machine learning, AI, VR, and now blockchain. And even though big data is not so clearly visible, it's still somewhere there. It's usually underneath. And new tools are still being released together with new versions. And to show you how many of such different solutions were created, let's start with a small quiz. So, who knows what is a seahorse? And I don't mean here an animal. Anybody? So this is a tool for defining some Spark jobs in visual manner. And next question, who knows what is an Azrael? And to be honest, I also didn't know that, because it appeared to be a Pokemon. There's a quiz called Pokemon or Big Data, where you get a name and you have to guess. Is it a big data technology name or a Pokemon name? And as you can expect, it's pretty hard to win. And to show you more, there's a repository called Awesome Big Data, and you can find their list of different big data related technologies divided into different groups. But it's not only about tools, but there are also scientific papers which are usually a base for those solutions. And this list is also pretty big. So what is really big data? So there are many definitions. Some mentions 3 Vs, 4 Vs, 5 Vs, even 6 or 7 Vs. But let's focus on basic 3 ones. So there's volume, velocity, and variety. We're having large volumes of data to be stored and processed, gigabytes, terabytes, petabytes. There's high velocity. This means that data might be coming to your system very fast, and it might be needed to be processed in real time or near real time. And there's variety of data formats, because you might be processing images, text, videos, and others. But I'm mentioning large volumes, high velocity, but what does it mean? So basically, there's another definition, quite simple, saying that when you build a system, there's a very specific moment when you can scale up more vertically to do your calculations in reasonable time. Moment when you have to switch to different approach, to tools running in clusters, and actually to big data tools. And people start using actually big data tools too early, because there's a hype, because they are fun, and big data tools bring some complexity, because you have to run a cluster, you need to have someone who will spawn those nodes, who will set up everything. And what is more, when you don't have really big amounts of data, and you can fit everything in memory, computation in memory on single node will be always faster than network communication between nodes. And also often models and algorithms designed to run in clusters may be less effective. So just be careful. And people ask, so what are really the big data use cases? And actually there are plenty of them, but some are not so obvious, because often when you have a lot of data, you don't really know what is valuable in them. And because of that, there are other domains like data science and machine learning, which tries to discover valuable things and then create models which are able to predict some things in that data. But basically, we're having, for example, IoT. So basically having a lot of devices, hundreds, thousands of devices reporting periodically, can give you billions of records stored per year, for example. And then those areas more related to machine learning, like user behavior analysis. So you might be gathering information about how every user uses your website, what clicks, etc., everything. But this can be also applied to movement of people in shops, for example, if you can track people in shops. Then recommendations. So all those emails which are sent by eBay or Allegro, like you might be interested in some groups of products. Then there's basket analysis. So if you add something to basket in an online shop, you may get some recommendations saying that people who buys this also buys other things. There are ads on websites when company tries to profile you, to try to find the best ad for you to maximize probability of clicking. Predictive support. And in this domain, basing on some readings from different sensors or some monitoring information, it tries to predict different failures by finding some minor differences in value outputs. And also there is fraud analysis, like discovering some fraudulent transactions, some invalid value-added tax returns, etc. Everything related to big data. And we're in Krakow, so everybody knows problems with air pollution. And now let's imagine that we're going to try to solve a problem with big data tools and methods. So basically imagine that you have thousands of sensors located in the whole country, or let's say on a whole continent, and they would be reporting some data points, some temperature, humidity, informations on chemical compounds. And to make this more challenging, let's say that they could be reporting quite often, for example, every 5 minutes. And if you will multiply all those numbers, you generally get billions of records per year. And so first, how can we store such amount of readings? And when we hear topic of storage, first we think maybe some databases, maybe relational one. And relational databases actually scales good vertically. So if you can add more memory, CPU, etc., they scale great. But when it comes to horizontal scaling and building clusters, then some limitations may appear. And I have noted down some limitations from documentations of a few relational databases. And these are as follows. For example, you can build cluster of maximum 48 nodes. Is 48 big or small? We're going to see in a moment. Then you may have some read-only nodes. So for example, you have only one node to which you can write and multiple from which you can read. So there is some primary and secondary replicas. But this way you can scale writes. And if you would increase number of sensors, we would need to also scale writes actually. Cross-charge joins might not be possible. Auto-increment IDs also often not available because it's expensive to have such counter ID incremented in cluster environment, in distributed system actually. And distributed transactions are usually possible, but expensive and not recommended. And basically this can work, but the thing I wanted to show you is that you won't get a whole set of features you are used to. And why? Because basically relational databases were designed to run on single nodes, and then they were just adjusted to run in clusters by limiting some functions. And why does it work this way? Because basically cluster is a distributed system. And there are some laws which apply. For example, there's a Kappa theorem or Brewers Theorem. And it says that in distributed system, you can satisfy only 2 of 3 qualities. So there's consistency, availability, and partition tolerance. And consistency means that when you perform a write to one node in a cluster and you read from different one, you will get the consistent answer. So you will get this value which you have just written. Then availability means that when you communicate with some node with the cluster and it replies to your request, you can also perform some writes. And partition tolerance means that if you have some network partition, some split brain scenarios, meaning that your cluster gets divided into multiple parts which can't communicate with each other, then this system can still function. And relational databases focuses mainly around C and A, but it depends. And this reflects on those limitations. Because, for example, we had this node this write node and read-only nodes. So you have there a synchronous replication. You're communicating with one node to write something, and it synchronously replicates it to secondary replicas. And it's related, for example, to consistency, because you want to get the same answers. And there is, of course, another group called NoSQL. And basically, this group offers different data models which might be easier to scale in clusters, but at the same time, in many cases, they are just more simple with less features. But also at the same time, not all of the NoSQL databases are actually designed to run in large clusters. So we have different data models like key value. So there's just a map where you store some value under a key, and this value can be an object, some list, some primitive, but you can query that data usually only using that key. So for example, Redis. Then there's a second group, sometimes called key map, sometimes they are called columnar databases. It depends on the definition. But basically you have there some tables, not connected using any relations, but columns in that tables may have sometimes some additional level of nesting. For example, you may have column with a collection inside, and this collection may have some elements with predefined schema. Then document databases. So you have collections where every document in collection may have different schema. Graph databases, basically designed to analyze some relations in graphs, to do some deep first search, etc. And multimodal, which tries to aggregate different models together, like Orient tries to combine a graph together. In this graph, in nodes, you have tables, for example. And to compare to that 48 nodes from relational databases, biggest Cassandra cluster, according to data from last year, was deployed at Apple and contained over 115,000 nodes storing over 10 petabytes of data. So it was pretty large. And with SQL and NoSQL, you usually encounter two acronyms, ACID and BASE. So atomicity, consistency, isolation, and durability. So basically with relational databases, you get usually transactions, but those transactions are not always needed. For example, for storing simple readings, you don't need transactions. So there's also another acronym called BASE. So basically available, this just refers to the A from the Kappa theorem. Soft state means that your database state may change even when there are no interactions with it. Because some asynchronous replication might be running in the background or some repairs might be running, but basically state can change on itself almost. And there is eventual consistency, of course, meaning that your data might be not consistent. And this is a moment where all the managers start screaming, saying that your data must be always consistent. But in practice, this means that your data might be inconsistent, for example, for 5 milliseconds. And why? Because basically you're having some asynchronous replication between different replicas in your cluster. And this means that finally your data will be consistent. Usually this won't take too much time, but if you have some network partition, of course you have first solve network issues, and then it will get consistent. And there's one more group, actually, and this group is pretty new, but first, it was first mentioned in one of the scientific papers in 2011, and it was called the NoSQL. And this group actually states that there are many solutions in that group, but most of them actually offers the ANSI SQL and relational data model. And at the same time, they have ACID transactions, and they are designed for online transaction processing, so to have some short reads and writes, not the longer analytical queries. And at the same time, they offer horizontal scalability, so they look perfect, but if you look at most common names in this area, like Google Spanner or F1, or CockroachDB, which is actually based on a Google white paper, and you can find some performance benchmarks. And I have found one related to some not latest version of CockroachDB. And in that benchmark, single CockroachDB node was slower than single Postgres node from 2 to 7 times. So single node performance was much worse, but still you can deploy this in cluster, having multiple write nodes, so you can scale writes actually. And small warning, Cockroach states that first they wanted to implement the features and now they are working on performance. And from the time those performance tests was performed by some guy on a blog, they have released already CockroachDB 2.0 and I don't know what's its performance actually. And I have mentioned different groups of databases, but actually there's no single choice for your project. Because in air pollution example, we need to store readings, and readings are quite simple and don't require transactions. And they could be stored, for example, in Cassandra. Because the Cassandra scale is great and there are no relations, it can work. But at the same time, the devices itself, which report those readings, might be highly relational, because you may be storing some geographical coordinates or relations to some device parts, software version, etc. And you could still keep that data in MySQL. So finally, you get 2 different databases in your project, and it's pretty normal. So let's say that we would use MySQL and Cassandra together. And now, let's say that we have stored that data and we want to analyze them. So let's do some big analysis, like to calculate the average temperature from the whole country from whole year. And basically, this is area of batch processing. So this processing may take time. And it's rather not a matter of seconds, but minutes, hours. And it can include multiple data sources. So we would read Cassandra to get the readings, but we also could read the MySQL to get information on location, to know what is in this country. And you can have different data types, and basically this includes a big batch of data. And when I'm talking about batch processing, I have to mention one algorithm, the MapReduce. And MapReduce originated at Google, then included also in open source implementation of Apache Hadoop. Basically, it's a way to do some computations in clusters in effective way. So there's a basic example of word count, where you try to count numbers of occurrences of words in a text. So let's say you have some book on input. We split this book to separate lines. And every node in cluster gets some lines to process. And this node performs some mappings, so maps a line to tuples of a word and number 1. Then there's a shuffling, in which data is moved between nodes in a cluster. And when you have the same words on the same node, then you can perform some local operations, local reductions. And you have the result. And in solutions like Hadoop, you had to do those steps explicitly. So in Hadoop, you had to explicitly define the mapper class, the reducer class, etc. But in newer tools like Spark or Flink, you just operate on collection-like APIs. So you have something which looks like a collection, and you apply transformations of grouping, filtering, mapping, etc. So it's much simpler. And now let's say that we would like to implement something else. That we would like to have this warning saying, is it safe to go outside today? Is air quality good? So to do that, we would need to actually analyze the live stream of those readings from sensors. And let's say that in our algorithm, we would take last 30 minutes of data, and we would need to group them by some location, by city or by district even. And we would calculate some average to just make those results more reliable. And this is a domain of stream processing. So actually here we would like to get results in real time or near real time. So rather it's a matter of milliseconds or seconds. And such processing does not have usually to end because you're constantly getting new readings and you constantly want to produce some information. And source for such processing are usually messages. So you can have some queues, some Kafka, some JMS as an input, some network socket, and others. And of course, there are some tools which implement stream processing models, and actually there are a lot of them. And these are even not all of them, because I have counted over 20 different ones. And what is more confusing, there are even 5 solutions from Apache itself. And each of them is a bit different. And so why? Because when we touch the stream processing area, it's basically a message processing, so different qualities related to message processing applies. And also it touches area, of course, of distributed systems. And there are only 2 hard problems in distributed systems. So exactly once deliver, guaranteed order of messages, and exactly once deliver. So let's take a look how this affects on those different solutions. So first of all, some theory. Time, because time is quite relative. When you get some reading, you can use different values of time. The reading itself may include time, so the device reporting some readings would have a clock and include timestamps. But if it doesn't have a clock, you may have ingestion time, which would be a moment you receive the message from the device, but they may be also processing time, so the moment you start actually processing this message by your algorithm. And if there are some network failures or your system is offline, then event time and processing time can be quite different. So for analyzing last 30 minutes of air quality information, rather event time would be better. And then we have windows. So I have set last 30 minutes. So this is a sliding window where we take new events and we discard older ones, and it's moving constantly. But you may have also some fixed windows where you just take 5 messages, next 5 messages, etc. Or there are session windows like related to user sessions. And now this out of order. So depending on the messaging system, you may get some messages out of order. So you're getting older messages after newer ones. And many of those solutions actually supports handling of such situations. And this works this way that you specify some margin, some watermark. So you can say that, for example, you tolerate some out of the order events up to 5 minutes, and after 5 minutes you will discard them. But still you can include them in your computations. And stream processing, of course, can include state for Windows and others. And now those main differences. So there is native and micro-batching approach. So in native approach, when your system receives a message, it is processed right away. And in micro-batch, it waits. It waits for small micro-batch to be aggregated for example, 100 messages or for 100 milliseconds, just to have this micro-batch. And this, of course, influences the latency and throughput, because with native approach, you get lower latency because you don't wait. And in micro-batching, on the other hand, you can get better throughput due to some optimizations. And for example, Apache Flink uses the native approach, and Spark in most versions uses micro-batching. I think that in Spark 2.3 they want also to have native approach. And then there are those delivery guarantees or processing guarantees. So there's exactly once, at least once, and at most once. So when you have exactly once, and let's say that stream processing system is reading events from some JMS queue, for example, it receives message, it starts some computations, it may produce some partial results, it may do some other computations, may produce other results, and when everything is finished, it will acknowledge message on JMS and it will be everything fine. But if the node fails during the processing, for example, between producing those partial results, then and you want to have exactly once processing, then you have a few choices. You may have a system which allows you to restart the computation from the exact moment the node has failed, but usually this may be not possible. Or you have to roll back transaction, which also may not be possible, depending what have you done with those partial results. So actually, exactly once is very hard to achieve and it's very expensive. So there's at least once, and at least once when the node fails during this computation, you just take the same message second time, and you may get some duplicates in the results. But it might be fine. But this way you get better performance. And third approach is at most once. So it's just a fire and forget. If the node fails during the processing, you just skip this message and take the next one. And APIs. There are some compositional APIs where you define the whole graph of processing manually. You have to define the inputs, outputs, and how data moves through the system. Or there are some declarative APIs where you just operate on collection-like structures. And for air quality system, you could use, for example, micro-batching because milliseconds wouldn't be scarce for us, milliseconds of delay. We could use, let's say, at most once, because losing some single reading related to temperature wouldn't be so scary. And we could use declarative approach because it is just more convenient for developers. And when I'm mentioning batch and stream processing, I have to mention two architectures. There's Lambda and Kappa. And in Lambda, when new data appears to your system, it is processed by two paths. There's a batch layer and there's a speed layer. And the batch layer contains a database with all of your data, and there might be some batch processing running. So basically, this processing can take hours. So it can take hours before the user sees this new data on some view. And that is why there is also a speed layer, which would include some heuristic, some less accurate algorithm, just to combine those less accurate results with batch processing result, and to be able to faster display something to the user. And for batch layer, you could use Hadoop or Spark, and for speed layer, you can use Flink, you can use Apache Storm, you can use Spark Streaming, and others. But basically, you're having two different engines underneath. And there is a Kappa architecture, and in Kappa, people have noticed that batch processing can actually be presented in form of stream processing. Because if you take the database table and you emit rows in that table as messages, then, and you apply appropriate windows, etc., you can actually calculate the same things on stream processing engine. So actually, the Apache Flink underneath is running in Kappa architecture, but outside they offer different APIs for batch and for stream processing. And in those two examples, we actually knew what we wanted to find in our data, that we wanted to calculate some temperature, to find some information, is it too safe to go outside today? But not in all those cases it's so clear. You may have some large amounts of data, and you might not be sure what's valuable in them. So you need to have someone who will analyze them, and usually would use some SQL language for that, for example. But if you have NoSQL database, you don't have usually the whole SQL language, only some SQL, for example, which is Cassandra query language. So there are solutions which helps you with that, because, for example, you can connect their different databases, and they allow you to query them together using some language, usually ANSI SQL, but not always. And they allow to do joins between different databases, and even more, they provide some ODBC or JDBC drivers, so you can interact with them together like they would be a single SQL database. So for example, you can take the Facebook Presto, where you can connect MySQL and Cassandra. You can have JDBC driver and connect them there's some Tableau or Power BI or other business intelligence tools. and it would see those two databases as a single relational one. So it can be pretty handy. And I have to mention here machine learning, of course. And many of those tools support some machine learning algorithms. But be careful here, because those tools designed for clusters usually includes only those algorithms which are possible to scale in cluster. So there might be other variants, but also you get less number of algorithms. And if you would like to just learn machine learning or get the best possible results without having large amounts of data, then you should start just with some standard single node tools like Python or R language and others. And resource management. So you can have data center, let's say, with 20 machines. And then you want to deploy there your application. Let's say you want to have 3 instances of your application, some web application. And then you want to assign that application some resources, some CPU, some memory. And then there's another application, there's MySQL to deploy, there's a Cassandra cluster to deploy. You may have some other things. And you have somehow to manage those things in a whole data center, and at the same time you want to minimize the costs, to maximize the utilizations of the machines. And of course you can do this manually to try to calculate will those two things fit on a single node, but you can use some resource managers. So there's, for example, Yarn, which originates at Hadoop and basically is intended mainly for Hadoop and some batch processing and stream processing jobs. But there are more general tools like Mesos or DCOS, which is based on Mesos or Kubernetes, which basically manages your whole cluster. So you can define that you have some service which needs some resources, and it will basically allocate everything so that everything works and it is optimally aligned. And if one node fails, it will just reallocate the services. And some small sample from the DCOS dashboard. So you get a number, how big % of your CPUs is actually used in the whole cluster, and how much memory is free in the data center. And also what services are running, what jobs are running, etc. And I have shown you today many different solutions, many different approaches of event times, processing times, and others. But if you would like to start your journey with big data, where you can actually start? And of course, it would be the best if you have some problem which would be interesting for you to solve. But this doesn't happen too often, especially to have big amounts of data for that problem. So there are some websites which includes free and open big data sets on which you can operate. So under this Quora link, there are over 20 sites, I think, which includes different data sets. You can read, of course, the awesome big data repository. Maybe some technology would be interesting for you, or just the scientific paper which explains how those things works underneath. And there's, of course, the more marketing approach, the SMAC stack. And SMAC is acronym for Spark, Mesos, Akka, Cassandra, and Kafka. So you have Spark for batch and stream processing. You have Mesos for resource management. But there's also Akka for building some REST APIs, Actor Model, Akka Streams. Cassandra for storing your data, and Kafka for data ingestion or some message passing. Some articles. First link is about Lambda architecture, second about Kappa architecture, and 3 links related to comparison of different stream processing tools, but also about those theoretical topics of different types of the windows, watermarks, etc. And actually, that's all for today. If you'd like to get some stickers from Software Mill or Scala Times, just grab them when leaving. They are on the table. And do you have any questions? Okay, it's the lunch time. Oh, there one question. This one? Yeah. Yeah, so if there are no questions, just go for the lunch.